Hello, this is Lazarus at telecomTech, where telecom and networking technologies are simply explained. Today we'll be simply explaining a multi-area OSPF deployment. Take a look at my free 27-page career roadmap for network and telecom professionals. It'll help you make decisions concerning the next steps to level up your career. It's free at my website at the link in the description below. And as always, if you like what you see, subscribe, like, and hit the bell icon. Now, one of the things that makes OSPF such a scalable and efficient routing protocol is its hierarchical nature. OSPF defines areas, which helps to manage and organize both routing advertisements as well as network topologies. Our topology will consist of this here. We have 4 routers and 3 areas. Router 1 here is an area border router, or an ABR, because it has one interface in the backbone area and another in another area. For the same reason, R2 here is also an ABR. Now, loopback 0 of R3 is outside of area 1. Now, notice that I've drawn this interface outside of this ellipse, which defines area 1. Practically speaking, this means I'm not directly advertising this subnet via OSPF. It'll be injected into OSPF, as we will see. This means that this route here is considered an external route. This fact makes R3 an autonomous system boundary router, or an ASBR. The whole OSPF topology is considered a single autonomous system, so any routes learned from outside of this area are considered external. Now, this loopback on R4 is inside area 2, which means that it is being advertised directly using OSPF. So R4 is not an ASBR. We'll see how this distinction appears in the OSPF routes that are shared and how they are displayed in the routing table. Now, before we get into the configurations, let's first express some rules concerning areas. Let me just say a few words about the rules that govern the way OSPF areas are implemented. Area 0 is the backbone area. All OSPF topologies must have a backbone area. Otherwise, OSPF will not function correctly. All backbone areas must have at least one router that is connected to the backbone area. In other words, this is not acceptable. As you can see, Area 2 is violating the rule because it does have an ABR, but that ABR is not connected to the backbone area as well. Now, this isn't acceptable either because there is no backbone area. There is no Area 0. Now, this rule actually results in all inter-area traffic traversing Area 0. In other words, if you want to go from a location in Area 2 to Area 1, you have to go through Area 0. Now, this setup is correct as it fulfills this requirement. Okay, let's go back to our original topology and see what we need to do to set this up. To make things easier, I have used a specific convention for my IP addresses. The subnet within Area 0 has 0 in the third octet. Similarly, the subnet in Area 1 has 1 as the third octet. And for Area 2, we have 2 in the third octet. Also, the fourth octet for each interface on the routers is the same as the router number, R1, R2, R3, and so on. At this point, the IP addresses are all configured on all interfaces, and the loopback interfaces are up and running. All we have to do is configure OSPF. Now, note that I am using Cisco IOS commands that are specific to OSPF version 2. When we talk about OSPF version 3, we'll see how those differ in a future video. So let's start with configuring router R1. First, we'll define the router ID. Remember, this is just a label. I'm using an address that corresponds with the name of the router. For R1, we're using 1.1.1.1. Then we issue these commands here, one for this network and one for this network. We also specify which OSPF area each one belongs to. This configuration, by definition, makes R1 an ABR because the network on this interface is Area 0 and the network on this interface is in Area 1. Let's take a look at R2's configuration, which is similar. Here we assign a router ID, and then we issue these network commands with these network addresses and OSPF areas. Similarly, R2 becomes an ABR for the same reasons. Now let's take a look at R4. Here we have the router ID once again, and then you can see that we are using the network command for this subnet here as expected. We are also choosing to advertise the network on loopback 0 using OSPF as well. So this here becomes an OSPF learned route and is advertised in OSPF. Now let's configure R3 and see how that configuration differs from R4. The router ID is configured again, and this network is advertised using OSPF. And then we have something different. This redistribute connected command will take all connected networks that are not already being advertised into OSPF, and it redistributes them. This means that the 10.10.10.0/24 network, which is a connected network, will be injected into the OSPF domain as an external route. This fact makes R3 our ASBR by definition. And that's it. Now let's take a look at our routing tables. First on R1, we can see the 10.10.10.0/24 network is being advertised as an external route. This E2 here means that this is an external type 2 route. When we redistributed, we didn't specify any additional parameters, and a type 2 route is the default. You'll also notice that the cost of a type 2 external route is 20. Now, because this is a type 2 external route, as it is propagated further into the OSPF domain, this metric of 20 will remain the same. I won't explain why here, but we'll talk more about external routes in a future video. Just keep that in mind as we look at other routing tables. You can also see that the 11.11.11.0/24 network is considered an inter-area route, which is indicated by the IA. This means that it belongs to another area, not the local area. Similarly, we see that the 192.168.2.0/24 network is also seen as an IA route, since it is in Area 2. These networks here don't appear in this output because we're only looking at OSPF learned routes. These are directly connected networks to R1. And if we were to view the whole routing table, we would see those as well. There are no intra-area routes here, meaning routes learned internally to Area 0, because within Area 0, R1 has not learned about any routes that are not directly connected to it. So this is expected. Let's take a look at R2. Here we see that the 10.10.10.0/24 route is learned as an E2 route, as expected, with a cost of 20. Remember, that 20 remains the same as it is being advertised throughout the whole topology. And R1 is advertised as the next hop IP for that route. Here we see a route to 11.11.11.0, and we see that it is an intra-area route because it comes from within the same area, specifically Area 2. And the next hop is R4, as expected, with a cost of 2. We also see the 192.168.1.0/24 network, which is this network here in Area 1, and this is seen as an inter-area route as expected. Now let's look at R3. Here we see this network, and this network, all appearing as inter-area routes. This is correct, since these routes exist in other areas, but none of them are external routes. You can also see the costs here are as expected, a cost of 2, 3, and 4 to reach each of these networks. Finally, let's take a look at R4. Here we have an external route for the 10.10.10.0/24 network. Specifically, it's an E2 route as in all other routing tables that we saw. And we see the same cost of 20 throughout the whole topology. The other two routes are inter-area routes, which are these networks here, with the cost as expected as well. Now, understanding what you see in the routing tables, especially when it comes to a multi-area network topology and the restrictions involved, helps out a lot when you're designing networks, as well as when you're troubleshooting. Well, that's it for today's video. I hope you found it useful, and if you have, please click that thumbs up button. Please check out my website and register for my newsletter. You'll find the links in the description below. And don't forget to subscribe to the channel to get updates to newly published videos. I'm Lazarus at telecomTech. I hope this has been helpful for you, and I'd like to thank you for watching.